Hi, today we will look into the design of the multi-plate clutch. Let us look into the question. The 10 kilowatt power is transmitted by multi-plate clutch at 750 rpm. Actual intensity of the pressure should not exceed the standard values. Due to space limitation, the external diameter is restricted to 240 mm. The duty cycle of the multi-plate clutch is 30 times in 8 hours. Design the multi-plate clutch. Determine the following: number of plates and inner radius. Design the input and the output shaft. The clutch has 6 number of springs. Decide the dimensional features of the spring. Design of the lever. Let us look into the answer. The given data are as follows. The power is 10 kilowatt, speed is 750 rpm, the overall diameter of the clutch is 240 mm, duty cycle is 30 times the clutch is operated in 8 hours. Application is not given, so we'll assume application as machine tool. There are some important parts of multi-plate clutch. For example, the input shaft and the output shaft, clutch plates, friction plates, spring and lever. Now we look into the figure. As we can see in the figure, there is this particular part is called as input spline shaft. So it's a spline shaft, and here we can see output spline shaft. So the type of shaft here we can see used in the multi-plate clutch is called as split shaft. So the shaft is divided into two parts. Now the overall dimension of this clutch box is given as 240 mm. So that is given in the question. We have springs used at the above and the lower part, and as given in this question, 6 of springs are used here. The clutch box has some thickness which is showed by TC, thickness of the casing or the box. Now we have some clearance between the box and the plates we have. So the clearance of one side of the clutch box has a clearance called C. It consists of levers, and the levers actuate and try to disengage the pressure that comes on the plates. There are two friction plates, as you can see here. The green color, this is one friction plate, the whole thing, and the other friction plate. We have clutch plates here, so we have 3 clutch plates, 1, 2 and 3. The clutch plates are bolted together and with using nut and bolt, and at the end we have a spring that is used to maintain the pressure. As we know, the clutches are generally in engaged position. That means the clutches help the power to be transmitted from the engine to the machine tool. The plate diameter is given as small d max, so that is the maximum diameter of the plate which we need to identify. Now, as we have gone through this layout diagram of the multi-plate clutch, we would like to see how we go with the design. So to find out the different parameters of the multi-plate clutch, we need to first find out the service factor. The service factor is known in the design data book as factor based on working condition. It is denoted by KW. Now KW is a combination of K1, K2, K3 and K4. So to find out K1, it depends on type of driving system. So if electric motor is driving the system, then the factor K1 becomes 0.5, and this selection is done from PSG data book 7.90. Now when we go to the K2 factor, which is depending upon the type of system we are using, so we have assumed the machine tool to be the system, so K2 becomes 1.25 using the table 7.91. K3 is a factor based on the RPM. Since the clutch is operating at 750 RPM, we will be finding out K3 on the basis of that. But when we look into the table of 7.91, we'll see that for 620 RPM, the speed, the factor given is 0.25, and for 1000 RPM 0.32 is the factor, but there is no factor given for 750 RPM. So after interpolation, I found out K3 to be 0.274. Now K4 factor depends upon number of engagements in 8-hour shift. So during its working time of 8 hours, the particular clutch will be operated 30 times. So according to this number 30 times, the K4 factor becomes 0.75, and the selection is done from the table which is shown in 7.91. When you try to add this up all together, so KW becomes 2.775. Once I found out the KW, I can try to find out the design torque. To find out design torque, I need to find out what is MT. So the formula for the MT is given. So 10 is the kilowatt that is given in the question, 750 is the RPM. So because they have multiplied this factor 97400, we can get the value in kgf centimeter. So it comes around 1298.66 kgf centimeters. When you convert it into Newton, it becomes as 129.866 Newton mm. Now to find out the design torque MT, we need to multiply kW with the torque that we have found out. So when you have multiplied and calculated, the design torque comes as 360.38 Newton mm. And when you try to convert it into kgf centimeter, the value comes around 3603.8. Now let us look into the input shaft calculations. To find out the input shaft diameter, first we need to select the material and for the material of the shaft I have taken it as C45. The material for the input and the output shaft, let it be same, so assume it like that. So I have selected C45 because the material is of low cost and it is easily available, and a general shaft material. Now SUT is 710 Newton per mm square according to PSG data book 1.9. Taking factor of safety as 4 for reversed and repeated loading according to VM Fairs, I have taken the FOS factor as 4. So the sigma T can be calculated as SYT by FOS. So SYT calculated is 355 and the factor of safety is 4. So sigma T comes around 88.75 Newton per mm square. To find out the design shear stress, it is half the times of the design tensile strength. So we can find out as design shear stress as 443.75 kgf centimeter square. Now after finding out the design stress values, okay, so the same formula which is given in the design data book I would be using. So DS1 is cubed under root of this particular parameters. So I know what is kW, that is power, and small kw, that is the operating factor. So my DS1 after calculation comes around 3.455 centimeters. I can convert it into mm and make a round total of it, which comes around 35 mm. Now I would like to find out the diameter of the output shaft. So I've assumed whatever diameter I have taken for the input shaft, it can be same for the output shaft as well. Now one more thing that can be observed is the shaft that is used for the multiplate clutch is spline shaft. Hence I'll go to design data book 5.30 to this particular page number to select a spline shaft. Since both the shaft are of the same dimensions, I will try to select a spline shaft which is close to this value called 35 mm. For exact 35 mm there is no particular spline shaft that is available, but shaft that is very close to 35, that is 36 mm is available. Hence I'll be selecting the spline shaft with the designation 8 into 36 into 40 mm, where 8 is the number of splines as you can see in the figure. Okay, 36 is the minor diameter and 40 is the major diameter. So we can see here D major, that is the 40, and 36 is the minor diameter. 7 is the width of the spline as you can see here, B. Okay, so that is the width of the spline. So all this information I have collected from PSG 5.30 based on DS2 calculations, that is 35 mm. Now let us try to decide the design of the clutch plates. Now the material for the plate can be plain carbon steel as recommended in the design data book 7.89. Friction material of the clutch plate can be compressed asbestos on steel. So this material also is recommended on 7.89. We will be taking recommended values because the connected values with this material is given in the design data book. We know that in today's world many of the countries have banned asbestos. Asbestos are not used as the compressed or the friction material for clutches in many countries. So the alternative is a word called organic. Now organic material is a substitute for compressed asbestos on steel. So it is generally made of fiberglass, silicon dioxide and some other materials. When you need a coefficient of friction much more that is available from organic, we select Kevlar or ceramic materials has many metallic compounds. So this is an alternative to compressed asbestos. Number of friction surfaces. Number of friction surfaces is represented by I, and the formula for that is given in the PSG page number 7.89. In this formula we know what is MT and design MT, and we know what is PA. Now PA is allowable pressure between plates which we need to calculate. Now PB is basic pressure. This both the terms come from design data book, and the formula and the relation PA is equal to K into PB is given in page number 7.89. So we need to find out what is K and we need to find out what is PB. Now B is a dimension that is used in this particular formula of I minimum, that is R max minus R minimum. So we need to find out what is R max and we need to find out what is R minimum. For coefficient of friction with respect to asbestos, the range lies from 0.45 to 0.35 as given in the PSG design data book 7.97. So I select 0.4. Okay. Now in this particular figure we'll try to find out what is R minimum and D max. In this particular we can see that D overall is given as 240 mm and D max is the diameter of the plates, C is the clearance and TC is the thickness of the casing. We need to find out what is R minimum and R mean. We will use this following figure and try to find out what is D max. Clearance we can assume as 1 mm and TC lies somewhere between 2 to 5 mm, so we can select TC as 4 mm. So from the figure we can see that D overall is equal to D max plus 2 times the clearance plus 2 times the casing thickness. Now we have taken 2 times the clearance because there will be clearance at above and at down part of the clutch box. Similarly, there will be casing thickness at top and bottom of the particular clutch blocks. Therefore, we have taken 2 times clearance and 2 times of casing thickness. When we substitute clearance and casing thickness and D overall, D max comes around 230 mm. Now when we try to find out R max, it comes around 115 mm. So we now know what is the maximum radius of the plate. After knowing that, there is a relation that we can that is given in PSG 7.90 between R max and R minimum. So I have taken R max as 1.5 times R minimum. Since we know R max, we can find out R minimum, which turns around to be 7.666 centimeter. Now we know R minimum and we can also find out R mean. Now R mean is average of R max and R minimum. Now we like to know what is called as small b. We look into the figure and you can see the distance of one side. Okay, this particular clutch box is symmetric and one side of the clutch box and the part of clutch plate is given by small b. And the small b you can find out if you know what is R minimum and R max, because when you subtract R max from R mean, what you get is small b. So I have come up with this formula: b small b is equal to R max minus R minimum with respect to the figure. So my b comes around 38.34 mm, which is 3.834 centimeters. Now to find out number of friction surfaces, I need to know what is PA. Now PA is K multiplied by PB. PB is the basic pressure. To find out K, we need to find out the speed factor. We need to find out the speed with which the clutch is rotating. The small k is called as the speed factor. So when I try to find out the speed, it is pi dn by 60. So the diameter is 240 mm overall diameter. The speed is 750 rpm. The speed of the clutch with which it rotates is 9.42 meters per second. From the graph that is given in PSG 7.90, the k factor turns out to be as 0.62, which is dependent on the clutch speed. Now I assume that the steel plates are having dry running. So this is not the case of wet clutch. So in the design data book there are two values given for wet running and for dry running. These plates are running dry. So the values given of basic pressure PB is between 2.5 to 3 kgf centimeter square. Now I have taken PB as to be 2.5 kgf by centimeter square. Therefore PA turns out to be as 1.55 kgf per centimeter square. Now the formula of I mean is in kgf and in centimeters. So therefore I'll be substituting values in the same manner. I'll be putting the design torque in terms of kgf centimeter. After substituting the design torque, PA, B, mu and the mean radius which I have found, I minimum turns out to be as 2.627. Now if I round total 2.627, it comes around 3. But whenever I select number of friction surfaces, it has to be an even number because single plate will have two surfaces. Therefore I have taken the value as 4 and not 3, so that I have a even value. Now I need to find out what is number of driving plates. The formula for number of driving plates, which is represented by M1, is given in page number 7.90. So I divided by 2 gives me number of driving plates, which is 2. The number of driven plates is given as I by 2 plus 1. So M2 is represented by number of driven plates and the number of driven plate is 3. Once we have found out the number of driving plates and number of driven plates, I would like to check whether this combination is correct. Therefore, there is a check formula that is given in the design beta book at the page number 7.90. I is equal to m1 plus m2 minus 1. So when I substitute m1 and m2, the final value of I comes as 4. Now the value 4 is same as that we have calculated earlier. Hence the selection of driving plates and driven plates are correct. Now we'll see the orientation of number of friction plates. So we can see that the m1 what we can see at this particular point and m2 at that particular point, these are called as the friction plates. They are also called as driving plates, and hence m1 and m2 are written. Each friction plate will have two surfaces. One is this surface, the other is that surface, and these surfaces come in contact with the clutch plates so that the engagement happens and the power is transmitted. Similarly, if you can see, the next friction plate that is here also has two surfaces which will get connected with the adjacent clutch plates. Hence you can see there are two friction plates and there are three clutch plates. The clutch plates is represented by M2 and there are three discs. The friction plate is represented by M1 and there are two discs. So this particular number is required to transmit 10 kilowatt power. Now once we have found out M1 and M2, we'll try to find out during the power transmission how much heat is generated. Now heat generated, the formula is not given in design data book, but it goes like this: design torque multiplied by angular displacement during the slip and number of clutching operations carried out in 1 second. We know when the discs are operated, there can be a slip that can take place between these discs, that is friction plate and the clutch plates, and when the slip happens there is heat that is generated. Now if the heat developed is beyond the permissible limit, then wear and tear will take place, and hence to avoid that we have to see that the heat generated is within the limit. Now it is understood that the angular displacement during the slip for a single plate happens generally 1.5 times the revolution, and for multi-plate clutch it happens 1 revolution, that is 2 pi. So we'll be using this value to replace angular displacement during the slip. Number of clutching operations carried out in 1 second. In the question they have given us the number of clutching operations carried out in 8 hours. So we need to find out for 1 second, and hence the whole value is divided by 3600. When we try to substitute the design torque, angular displacement during the slip, and number of clutching operations carried out in 1 second, heat generated turns out to be as 2.35 watts. After calculating what is heat generated, we would also like to find out how much is heat dissipated. Now heat dissipated is given by this formula, which is available in the book called pKnag. We know what is H, that is outside heat transfer coefficient or forced breeze flowing coefficient. A is the area, Tc is the temperature of the casing, Ta is the ambient temperature, sigma is Stefan-Boltzmann constant, and again A is the area of heat dissipation. So it consists of, the heat dissipation consists of convection and radiation. So we need to find out the values for this and try to calculate heat dissipation. Now we know certain values, since heat transfer coefficient turns out to be as 25 watts per meter square Kelvin. Stefan Boltzmann constant, we are aware of that, and ambient temperature we can assume. So let it be 27 degrees Celsius, which turns out to be as 300 degree Kelvin. To calculate the area, we again have to focus on the clutch box. So you can see heat can be dissipated from the left hand side of the clutch box, the right hand side of the clutch box, which is circular in nature, and it can also happen along the width, that is the circumference. And hence I have taken the circular left hand side as pi by 4 d overall square. Since there is front side and the back side of this particular clutch box, which is circular in nature, I'll multiply that number 2 to it. To find out the circumference, I will multiply 2 pi rm into b. Now capital B is the width, the total width of the clutch box. You know that it can be pi d into b as well. Now to find out the width of the clutch, we need to find out how many discs are present in the clutch. We can see that the disc of the clutch can be identified by adding m1 plus m2 and considering some clearance in between them. We need to take care what is the thickness of the casing and some margin between the casing and the plates. So assuming few of the values, we can find out the width of the clutch, that is capital B. So some calculations are like that. I know what is m1 and m2. Clearance I can take it as 2 mm as earlier. Thickness of the casing is 4 mm, which we have assumed earlier, and margin I can take 8 mm considering both sides. Hence B, that is the width of the clutch, comes around 22 mm. Heat dissipating area of the clutch A can be given as follows. You know width and you know d overall, so area is calculated. So it comes around 107065.477 mm square. Now I'll try to equate heat dissipated and heat generated. When I equate that, I don't know something called as Tc, that is the temperature of the casing. Other values are known. I substitute the known values and try to find out what is Tc, which turns around as 300 degree Kelvin. Now that is 27 degrees Celsius. The thumb rule is that if the temperature of the casing does not surplus 60 degrees Celsius, then external lubrication is not required. Hence we don't have to design any lubrication system for this particular clutch box. Now to find out actual pressure between the plates, how much pressure is exerted between the plates can be given by this particular formula, and this formula appears in the design data book 7.90. As you can see, most of the parameters we are known, so we will substitute all these parameters which is known to us and try to find out the value of sigma, which is actual pressure between the plates. It can be seen that it comes around 1.1081 kgf centimeter squares, and this particular pressure that is developed between the plates is less than the allowable pressure PA, which is 1.55 kgf per centimeter square. Hence the pressure that is exerted to transmit power of 10 kilowatt is within the permissible limit. Hence the power can be transmitted safely. Now we'll try to summarize the different parameters that we have found with respect to the clutch plates. The Dmax value comes around 230 mm. Number of friction surfaces are 4. The inner radius of the clutch plate is 7.666 centimeters. No external lubrication is required. Actual pressure between the plate is 1.1081 kgf by centimeter square. Width of the clutch B is 22 mm and the overall diameter of the clutch is 240 mm as given in the question. So up till this point we have completed the design of the clutch plates. Now we'll look into the design of the spring. We know there are two types of springs, tension spring and compression spring. Since helical compression spring is used to apply pressure between the plates, compression spring would be a right selection. Application used can be assumed as machine tool. The material for the spring can be taken as 50 CR1 V23 and the sigma ut value for that is 1250 Newton per mm square. To find out the actual force that is applied on the spring can be found out this formula, which is given in PSG 7.90, that is Q is equal to pi sigma R max square minus R minimum square. Now we know most of the parameters, hence the actual force acting on the spring can be calculated, which comes around 255.78 kgf. Now after calculating the actual force, we'll try to find out the maximum force and the minimum force that will be acting. Now the maximum force P max is given as Q double dash and the minimum force is given as Q dash, and the formula to find out Q dash depends upon the actual force divided by number of levers. When you look into this particular table, which is not there in the design data book but has been found out by empirical relation, when your overall diameter is less than 200 mm, you can select number of levers as 4. If your overall diameter is between 200 to 400 mm, you can take the number of levers as 6. When the overall diameter is more than 400 mm, the number of levers can be selected as 8. Hence our diameter is somewhere 240 mm, which lies between 200 to 400 mm, so the number of levers can be 6. Hence Q dash can be calculated, which comes around 42.63 kgf, which is the P minimum. Now we are interested to find out what is P maximum. Now P maximum is K multiplied by P minimum, where small k is called as the engagement factor. The range for the engagement factor is 1.11 to 1.25. So select the value as 1.25. So since we know what is P minimum, which can be multiplied by the engagement factor, P max turns out to be as 53.2875 kgf. After we have found out P max and P minimum, we are interested to find out what is the stiffness of the spring, which is represented by Q. But to find out the stiffness of the spring, we need to find out what is the compression allowance. To find out compression allowance, we have the following data. Compression allowance is 3 mm for single plate clutch, and compression allowance is I multiplied by 1.3 mm for multi-plate clutch. After substituting the value of I, it comes around 5.2 mm, which can be approximated as 6 mm. Hence, we can find out the stiffness of the spring, which is also known as spring rate. So Q is equal to P max minus P minimum upon compression allowance. We can substitute the value and try to find out the spring rate, which comes around 1.7762 kgf per mm, which can be 17.762 Newton per mm. Now, after finding out the stiffness of the spring, we will assume the spring index. The spring index, capital C, is given by capital D by small d. Here capital D is the mean coil diameter, whereas the small d is the coil diameter. There is one more alternate formula for spring rate, which is Q is equal to capital GD divided by 8C cube into N, where for the given material modulus of rigidity is 0.8 into 10 raised to 5 kgf per centimeter square. So we'll try to find out the parameters that is unknown to us. To find out the N, that is number of coils, we need to find out the shear stress on the spring. So the shear stress formula is given in PSG 7.100. To find out shear stress, we need to find out first Wahl's stress factor. Now after substituting the spring index, the Ks comes around 1.2525. Now after finding out Wahl's stress factor, we can try to find out what is the design shear stress that comes on the spring. Now it depends upon the cycles that the spring needs to undergo. Selecting medium cycle, that is PSG page number 7.102, from that particular page we can take it as 0.325 by sigma ut. Here, to find out the allowable shear stress, we can consider the stress cycles are between 10 raised to 4 to 10 raised to 6. So for this particular stress cycle, the design shear stress is 0.324 multiplied by sigma ut. Now we need to find out the diameter, that is mean coil diameter. So we know the allowable shear stress. So after knowing all these parameters, I'm substituting them. We can find out small d, which comes around 5.0173 and can be approximated as 6 mm, which is called as the coil diameter of the spring. Once the coil diameter of the spring is calculated by using the spring index formula, we can find out the mean coil diameter of the spring, which is 36 mm. After finding out that, we can substitute the known values in the equation of spring rate, that is capital G multiplied by small d upon 8 into C cube into N. The unknown in this particular formula of spring rate is N, and hence the N, which is known as number of coils, can be 16 after approximation. Now for square and ground ends, the total number of coils required for the spring is N plus 2, which is 16 plus 2, which turns out to be 18. By this point we have finished the design of the spring. Now when you look into the design of the lever, we'll first have to select the material for the lever, and the same material for the shaft can be selected for the lever as well, which is called as C45. For example, the design tau shear stress is 44.375 Newton per mm square. Design of the lever, we can look into this figure and we can see that Q dash force is acting here at this particular point, and Q double dash is acting at this particular center of this particular circle. Now when we take movement with respect to O1, which is this particular brown color point, we can see that Q dash multiplied by A is equal to Q double dash multiplied by L. Hence this particular equation is obtained. Now looking into this equation, Q dash into A is equal to Q double dash into L, we can find out what is L using empirical relation. L is 0.8 times D overall, so that is 0.8 into 240, that is 192 mm. A can be found out using L, since A is 0.3 multiplied by L, which is 192. small a comes around 57.6 mm, which we can round total as 58 mm. The relation a is equal to 0.3 multiplied by L comes from the empirical relation. Now we have this formula called as H2. Now H2, when you look into the figure, is the cross sectional area of the lever. So the cross sectional area of the lever is H2 multiplied by B2. To find out H2, this particular formula is given in the design data book. That is cube under root of 6 into Q multiplied by A upon design sigma B multiplied by psi multiplied by I01. Now we know many parameters from this particular equation. For example, we know what is Q, we know what is A, we know design sigma B because it comes from the material. Psi is something we can select from the design data book, where psi is B by H2, and since we have taken a square cross section, we can take the factor psi as 1. I01 is the number of levers used, and we have taken it as 6. When we substitute these values, the H2 comes around 1.186 centimeters, which is 11.86 mm, which can be round totaled as 15 mm. Since H2 and B are the equal, we can take B as well as 15 mm. After finding out H2 and B, we can find out the small d1 diameter that appears in the figure. So when you look into the figure, this particular circle is known as d1. To find out the diameter of that particular circle, formula is given in the design data book in this particular manner, where A is under root q1 dash square plus q double dash whole square. So after looking into this, we can find out A, which is 68.241 kgf. Now d1 is equal to 2 times under root of 2 into A upon pi multiplied by the design tau. Since we know A, we can substitute that, and d1 comes around 0.3128 centimeters. Now we can find out it in terms of mm, that is 3.128 mm, which we can round total as 5 mm. Up till this point, we have finished the lever design as well as the problem of multi-plate clutch.